Hey everybody, Lars here. Just figured I'd jump on real quick tonight. Hopefully this is a short one. And do a review of the first part of your Unit 4 slides, the part on sorting and searching. I'm going to start by bringing up our slides and just discussing sorting for the beginning. As you know, if you've read the slides already, and I hope you have, it's a weekend. I'm not going to make you code up a sort. I've probably told you this story before. If you're a young computer science student and you're going to university for computer science, when you take your first course, usually about a month and a half in, all of a sudden you are inundated by sorting. You have to learn how to do a bubble sort and a J sort and a quick sort. And for the 2 or 3 weeks there, sorting is the bane of your existence. It drives you nuts. And at the time, you don't know why you have to do this. And I'm sure it makes some people think twice about choosing computer science because, in effect, they're getting, bored out of their skulls. But later, when you get older and you get more into computer science, you realize what was going on, what the method behind the madness was. And it was so that computer science professors could show you the different efficiencies of different kinds of sorting algorithms. Because what is a sort? You've got a list and you've got a group of items in it. And now let's assume that these items can be compared. And when they are compared, you can see one is greater than the other or one is less than the other. And what you want to do is put things in an order where if I have an item, everything to the right of it is greater than it and everything to the left of it is less than it. So it's in an order. It could be the other way around too. It could be ascending or descending. Now, you're probably wondering, well, why is that important? Because a computer is not like a person where an alphabetical list makes it easy to find something. But you'd be wrong. Sorting does make things easier to find, and we're going to learn just how much efficiency we can gain when we search through sorted lists versus searching through unsorted lists. But first I wanted to review sorting. And basically in this slide, that's all I do is I talk about what sorting is, and I tell you a little bit about the bubble sort. And at the end of the day, the bubble sort is just start at the bottom of the list, go up. Is this thing smaller than me? Okay, then we're going to want to switch. And then you switch. Then you go back to the bottom and you do it again. And you'll do it until you go down to the bottom and you go all the way up your list and everything is in order. Now, that takes a long time. It's not exactly the most efficient sort in the world, but I'm going to tell you about one that's worse in a second. Now, if you go to this website, sortingalgorithms.com, you can see all the different algorithms run. And somebody put up a nice video. I think David Eitenberg put up a decent video about this and shows all the sorts being run on YouTube. And you can watch them with, actual audio of the sort being run, which was actually pretty cool. So go to this page and look at these different sorts. And you can see the quick sort was very fast and very popular for a long time. I think it's the main sort in Unix systems, and it's also the sort used in C for the longest time. As you'll see when we go through the slides, Python uses another kind of sort called the TIM sort. And even though sorting has been part of computer science since the 50s, the TIM sort wasn't invented until the early 2000s, but it's used for Python. So go check out these different sources these different sorts, and when you look at them, you're going to learn that there's another sort called BOGO sort, which basically just says, is this list in order? And if the answer is no, it just randomizes it and then says, is this sort in order? No, and then just randomizes it. So the theory being, if you keep randomizing it one time, it's going to be in order and you're going to be okay. It's like if you put 50 monkeys in a room and have them write, eventually, if time is infinite, one of them is going to write Shakespeare. So I don't know how true that is, though. But that's the idea behind BOGO sort. And BOGO sort, I would be shocked if it does not win the award for the most inefficient sort ever. But go look at some of these sorting algorithms and see how they do it. Most, I think Quicksort is one of these, will take the data and partition it, and then order that partition, and then it'll merge the two partitions together in a sorted order. And they do a lot of smart things that are very efficient, and studying the algorithms that are used in some of the more complex sorts is a good way to learn about algorithms in computer science. But for our purposes, we're just going to learn about the quick way that you can sort a list with Python. And it is the easiest thing in the world. You create a list, and then you run a method on that list called sort. Boom. And it uses the TIM sort behind the scenes to sort the items in your list. And if, as you can see, I give an unordered list of numbers in my list, but then I run sort on it, and when I print it a second time, the numbers are in order. So that's a list of integers. I can do the same with strings. If you send sort a list of strings, the method is smart enough to realize that, oh, okay, I've got strings. I'm going to sort by alphanumeric, and it does so, as you can see down here. We will discuss the meths later. Now, what if I have a list that has mixed types? I have a name, I have a number, a name, an integer, all the way down the line, and then I try to sort that. What's going to happen if we do that? What happens if we do that is we get an error. Because one thing you have to make sure of before you try to sort something is that it's of the same data type, or it's of a type that can be compared. Because if you think about what a sort is you're going to compare something to something, and if it's bigger, then you're going to swap it. Well, I've got to be able to do that comparison. Now, you know, it's an old saying, but I can't compare apples and oranges. So if I have apples and oranges in a list, which I can have because I can have mixed data types, then I'm not really going to be able to sort it. If you move on in computer science and you learn about Java and you learn about some other things, then you could implement a thing called sortable and make sure your object, be it integer or float or some other data type that you create, has a way to compare itself to other things that are similar. So I think that's an interface in Java called comparable or comparable. So you can implement that later in the future if you get more complex and you keep going forward with computer programming. But right now, in this simple example, with just a regular list, you don't want to sort it if you have mixed types. But sorting is important because the more things we know about our data, the smarter we can be with our data. And here we go. I say right here why we care so much about sorting. We care a lot about sorting in the beginning of computer science education because it's a good way to show different algorithms. It's a good way to have students practice with code and do a lot of comparisons and swap variables and things along those lines. And at the very end of when we talk about searching, we'll talk about big O. Because even the small thing we're going to do, big O comes into play, and we'll talk about it. But the most important thing about sorting from a programming standpoint is that it makes searching very easy. Because if I know that I have a sorted list, when I search for something, I can do so in a very efficient manner, and we're going to look at that right now. If I'm looking for something in a list, what am I going to do? What does anybody do? What happens when you lose your keys? You start going backwards and you look where you were and you look everywhere, not in the couch, didn't fall down by the stairs while I was walking in, not sitting on my front car seat, not boom, boom, boom. So you look at everything, and if the item is in the list, you find it, okay? So that's okay if you've got a list of like 20 things and you keep searching, oh, it's in the 17th spot. Okay, boom. You've only done 17 lookups, as we say. If you look into your list or something, we call it a lookup. So I've only looked 17 times, but this is computer science, and specifically in data science, where you're dealing with, you know, data mining and big data and things like that. You could have lists up into the millions. And if you're searching for something that's in the 4 million spot, well, I don't want to have to look at 4 million things before I get to what I'm looking for. So that method of just running right through a list and looking at everything until I find what I want is called linear search, which makes sense. You're just going down a line if you think of your list as a long line of data. So that's one way to do it. Hey, I've got a list of numbers. Is 27 in that list? Look at the first item. Okay, let's say my list is called ZZ. ZZ of 0. Is it 27? No. Is it 127? No. No, until you get up to, say, 16, and then, yes, it is. Okay, I'm going to return 16. Because you never return the number you're looking for. You know that already. What you want to return is the index. You want to return the place in the list where that particular item is. So, linear search, you know how to do it. If we created a function, you would send the function a list and the number you're looking for. You would hop into a loop, and go through the entire list and see if that number is equal to one of the items. If it is, return the index. If it's not, we usually, when we write these search functions, we return -1, assuming you have a list of positive integers. Anyway, that's the way I did it. You're going to see that in a moment. But let's consider what we know about a list that is sorted, okay? Because then what comes into play is something called a binary search. And a binary search is pretty swift, because what a binary search is basically a computer science version of high-low. Let's say I've got my 20 numbers in a list, but they're sorted. So what can I do? I can go to the middle of the list, and I can say, is this my number? And if it is, great. If it's not, well, I know I've got a sorted list. So I can see if what I'm looking for is higher or lower than that middle number. If it's higher, then I can throw the entire lower half of the list out, because I know it's not going to be in that spot. And then I can take what's left, the upper half of the list, and I can grab the midpoint of that, the 75. And at that point, I can say, is this my number? And is it? Great. If it's not, well, then I can say it's lower. Well, then if it's lower, I can dump the lower half again, and then I only have half of that list. So basically, with a binary search, the fact that my data is sorted allows me, with every lookup, to cut my search field in half, which is incredibly efficient. We'll talk about that with Big O in a second. But as I use as the example here, if I've got a list that's 1 million long, and I'm looking for something that's in the upper half of the list, well, I'm going to have greater than 500,000 lookups before I even get near it. If I do a binary search, I go right to 500,000, and I say, is this the number? Yes or no? If the answer is no, your number is greater than this, then I can throw away 500,000 numbers that I don't have to consider. I know it's not down there because my list is ordered, and the number I'm searching for is greater than the one in the middle of the list. There's a better graphic I have here, yeah. Right here. Because my list is sorted, I can search for it in this fashion, and I can keep cutting my list in half until I either find the item I'm looking for, or if I get to a certain point where the high and the low are the same, then I know the number is not there, and I can return my -1. So this is called a binary search, and this is incredibly efficient. I mean, at the front end of big lists, you're throwing away half of the list every time you go through. That's insanely efficient. I'm going to show you that we're going to go through some number lists later, and you're going to see you can find things in like 10 lookups, where if you do it with a linear search, it takes hundreds of lookups. So it's very efficient. First, I think in these slides, I put the code for a binary search in there, but I'm guessing you can't see that really well. So I created a library called, what do I call, mysearches.py. Remember this. It may show up in an assignment. Wink, wink. So take a look at this code. And I coded up a binary search. Now down here I also coded up a linear search, which is the easier version, so we'll probably go through that first. And it's a piece of cake. Define lsearch, the number I'm looking for, and nums is the list that I'm going to search. Now, I create a counter. I make it equal to 0. And then because it's a linear search, I'm just going to go through the list. But I don't want to just iterate through the list without index numbers. I want index numbers because I'm going to have to return that index number. So I create a range, and I go through the list with range numbers. Because if I iterate through the list like I would any other list, well, then I don't really know the index number, and I can't return the index number. I could, because I could use the counter, but that's getting beyond things. So what do I do here? I say the length of my list, -1. Now I want to start at 0, so I don't put anything there. I'm just going to use the default. And then I grab the length of my list, -1, so let's say it's 500. So I'll be going from 0 to 499. And I'll say, is x equal to num, first item in the list, 0? If it is, I already found it. I add 1 to my counter, because I'm going to count how many times I do comparisons. And then I say the numbers found, and I say this, it took one pass because I went out already. But that rarely happens, unfortunately. Life isn't that nice. So usually the first thing you find isn't it. So I go down here, I increase the counter by 1, and then I go up to the top again. And I grab the next number. So is x equal to num of 1? Is it? Great. If not, boom. So I'll go through this loop, and let's assume that the number's in there. Let's say I grab a list of the numbers 1 through 500. I'll do that example. As a matter of fact, we'll do it right now. Let's say I say x equals L search. Well, first I got to create my list. Would that help, you think? I'll just call it ZZ. I'll say I want a list range 1, 501. First thing I don't want. And you remember that's the way we create a list with range. We have to cast it with list because range is a generator, but I really want a list. So let's search for, let's say, 345 in my new list called ZZ. And what's it going to return? It's going to return X. So let me print ZZ of X. And let's see what we get. Boom. Number found, 344. That's the index. It took 345 passes, of course, because it had to look 345 times before it got to 345. Okay? So, as we can see, it ran through this loop 345 times until it got to 345. Is x equal to num of 344? Yes, because it was 345. So then I add 1 to my counter, because that's a comparison. I've got to count it. Then I say that the number is found, and I print the index, and then I say the linear search took C passes. And then I return I. I return the index number. So that x equals that. So down here, I use x in my index when I reference my list item, and I print the number that I was looking for, because that's what searches usually return when you search lists, the index in the list where your item appeared. Okay? So that's the simplest thing we can do. That's a linear search. Remember, this is YouTube. So you can stop this video at any time and stare at that code and read it and see what I'm doing and understand how it works. Okay? Now, what's the second kind of way we can search through this list? Now, this is a sorted list, remember, because ZZ contains 1 to 500 in order. So, ordered list, I shot through, and it took me 345 lookups to find the number 345. Let's see if we can do better than that. Now I have a function called binary search. This looks like 40 miles of bad road. It's not. Stick with it, and you'll understand it. All you have to do is stay calm and read through the code. So what do? Same as linear search, I have a number to look for, and I have a list called nums. So I set up a variable called item. I make it 0. I have a low point. That's going to be the low bound of my search area. And I have a high point, which will be the high bound. Now, the first time through, low is 0, and high is the length of the number. So in our case, low is going to be 0, and length minus 1 of nums is going to be 499. And again, I set my C to 0. Now, I do this in a while loop because I want to say as long as low is less than or equal to high, which means that your lower bound and your higher bound aren't touching, and you still have a range, then keep going in the loop looking for numbers. So what's the first thing I'm going to do? Remember what binary search does. It takes a sorted list, and the first place it looks is the middle. So what would the middle index of this be? I create a variable called mid and make it equal to low plus high divided by 2. So in this case, it's going to be 0. 499 divided by 2. It's integer division, so I'm not going to get that 9 split in half. So the mid is going to be, what in this case? 249 or 250? I don't know. I'd have to do it. So then I take item, which I declared up here, and I make it equal to the item in the list, nums with the index 249. Now, as you can see, I commented out some print things for error checking purposes. You can use them, and then if your list is having problems, you uncomment this so you can print and watch things along the way and find out where your problems are. So, okay, I've split the list in half, and I've set the item to the item in the list where the index is in the middle of the list. Okay, understand that because that's an important concept. I have a search range defined by low, which is the index of the low bound, and high, which is the index of the high bound. I add them together, I divide by 2, and that's going to give me the middle of the list. So now item equals what's in the middle of the list, or in this case, the item at index 249. So what's the next thing I do? I say, is x equal to the item, which is a kill shot? I will have found what I wanted. If so, I print the number is found, blah, blah, blah. We'll get back to that because usually we don't find it on the first thing. Then I have an elif down here. It's not the number. Okay. Is what I'm searching for greater than the item? I mean less than the item? If it is, then I want to change my high bound and make it the middle minus 1. So in effect, what I'm doing there is I'm saying if the item is greater than what I'm looking for, that means the midpoint number is greater than what I'm searching for. So I don't need the top half of the list. So take high and make it equal to mid minus 1. So now the high bound of my list is going to be 249 or 248 minus 1. So now the next pass through, I'm not searching from 0 to 499. I'm not searching 500 numbers. I'm only searching 250 numbers. And I can do that because of what I know about the data. I know it's sorted. Now, let's say that's not true. If that's not true, if it's not the item and it's not less than, well, then there's only one choice left. It has to be greater than. So if it's greater than, what do? I change the lower bound to 249. So the next time through, I'll search for 249 to 499. I'll search only the upper half. Now, as you can see, in both instances, I increment my counter because they represent a pass or a lookup through the data. And that's what I'm counting. I'm using C to count lookups through the data. As you'll see when I do the assignment, assignment 2 is going to deal with searching. I ask you to tell me, hey, how many passes did it take? Because then if you know how many passes it took, then we can begin to analyze the efficiency of these things. And that's how I keep track of it. I just increment a counter every time I go through in these situations. Now, it doesn't happen 3 times, of course, because only one of these sections is going to be true every time through. Okay, so I come up here, cut the list in half. Is it the item? No. Higher or lower? All right. Come up here. Actually, I come up here. It's the if statement. Is this my item? No. Higher or lower? Cut my list in half. Is this the item? No. Higher or lower? Cut the list in half. And you keep doing this until you find the item. Okay? And if you find the item, if it exists in the list, you print number found. I click my counter because this is a pass. And then I print binary search took C passes because that's how many passes it would have taken. I give you my counter variable. And then I return mid, which is the index that got you item. Okay? So, yeah, I want to return mid because that's what gets you that. Now, if it's not in the list, I will run through this entire loop until low plops up over high. Okay? And then you'll know there's no range because it's negative. It will have closed, 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 and it will have flipped over 1. And at that point, I know, hey, I'm out of this business because now I know I've searched the entire range. Nothing is there, and I'll fall out of this loop. And when I fall out of this loop, then I say binary search took C passes because I want to know how many passes it took whether I find the item or not. And then I return a -1. You see, the -1 is only returned when you fail to find the number. Because if you find it, you're going to return the mid value. And then the function's over, the variables go away, like I told you last unit, and everything is fine in the world. But if I don't find it, then I want to return the -1, okay? This is not as complicated as it probably looks while you're staring at it right now. I beg you to just read it and read it carefully. Maybe as you go through some passes, chart the variables on a piece of paper and know what they're doing. But this is a binary search, and this lets you take a list that is however long, and every time you search through it, if you don't find the item, you are going to cut your search area in half. Okay? So let's go back to our list down here and see what we can see. Now I want to do X equals binary search. And I want to look for the same thing because I want to compare the efficiencies of the two. And I want to give it ZZ. And if it comes back with something, which I think it's gonna, I want to print ZZ of X. Okay? I know what we get. All right, look at this. Here's my linear search. It took 345 passes. Here's my binary search. Number found, 8 passes. I did 8 lookups. Think of the efficiency. Because every time I went through that list, I cut it in half. All right? We're going to talk about Big O in about 2 minutes, and that's log n. That is exponentiation backwards. That is efficient and fast, and a linear search is n. When I say n, I mean the size of the list. And you're gonna we'll learn about Big O in a second, but Big O is basically just a function of how efficient my algorithm is as the input gets bigger. So if my list is only 10, then n is 10. If my list is 1,000,000, n is 1,000,000. So if I run a linear search and I'm doing it with O of n, well, then I've got possibly 1,000,000 lookups with a linear search. Okay? With a binary search, it's only log n, which is considerably lower. Think about how big numbers get with exponents. Well, it's the inverse with log. Remember your math in 4th or 5th grade. When you did logarithms, what is it? It's exponentiation backwards. It's the inverse of exponentiation. So this is the kind of efficiency you get when you search through sorted data versus searching through unsorted data. So get a good look at this. Remember, hint, hint, nod, nod. This is YouTube. Pause this and look at this code, okay? Because this is a binary search. If I'm not mistaken, you saw this in Zell. I believe the chapter 13, I think it was, which is a tour de force of the computer science stuff we're looking at, because you have sorting in there, you have searching in there, you have recursion in there. I don't know if they mentioned Big O, but I believe this is the way that they do it in the book. I don't know if they code up a linear search in the book. They might not. I don't know. I read it a couple of weeks ago. So that's the step if you want to search through a list with a binary search. Now remember, you can only do it with sorted data. If you give a binary search unsorted data, well, then you have no idea whether you're going to find something or not, because it's assuming it can do this the comparisons. And you can't do the comparisons with unsorted data, because then one thing could be in another spot. You could have 10,000 in the 3 spot and 3 in the 20, and that's the algorithm makes no sense at that point. You're assuming sorted data when you look at a binary search like that. Okay, so that's a binary search. I am not going to put this in Sakai because you are going to know that tomorrow, because I'm going to release the second assignment. And the second assignment is basically going to be take a big file of random numbers, clean it up, and then I'm going to have you search for some numbers in the list. And I'm going to have you search using a linear search, and I'm going to have you search using a binary search. So you just saw how they worked. You just saw how the code was there, and it was written boom, boom, boom. So do not say I did not give you the resources to do the homework. Now, the last thing we want to do, what did I do here? So I showed you the sort, and then, say you see those lines that were, remember those lines that were commented out? This was me when I didn't have them commented out, so I could show you each pass. So make sure to read these slides and read them carefully. Okay? And then, I talk about the binary search, and then I don't think, did I code up the linear search for this? No, I just used the binary. Suffice it to say, a linear search is nothing. You've done linear search already. Take a list, jump into a loop, and look for something. And if you find it, great, return it. If you don't, then just go to the end of the list and say, sorry, didn't find it. It's not brain surgery at that point. But and sometimes this is done with sorting, but in this search case, it's a good time to talk about Big O and the analysis of algorithms. So we go into Big O, that's Oscar Robertson, that's Big O, never mind that nonsense right now. And this is me blabbing, blah, blah, blah. When you think of Big O, just think of it as a function. And it's a function that looks at the efficiency of an algorithm as input gets bigger. That's all it is. So you'll see O of 1. 1 is a constant. That means no matter how big your data is, that algorithm is going to run in the same time every time. Okay? So if you have something that you give it a list and then you print hello world, well, that's constant Big O, because it doesn't matter how big your list is. You're always going to run in the same amount of time no matter what you do. Then you have O of n, which is basically what a linear sort is. N gets a whole bunch bigger as your list gets bigger. And if you have something where you have to look at every single item, then something that is O of n will get bigger and bigger and bigger. Now, you'll also get situations where you have to delve into n, where for every item, you'll have to check 3 other things. That's where n gets bigger, and you could get n squared. You can get n factorial, which is a big problem in computer science, and some other things. But you can also get something like the binary search. And I chart some of them here, or actually I stole a chart online here, and show you some of the different Big O functions charted up for you so you can see how they look. Binary search is, yeah, I talked about it here. Binary search is log n. So it's the opposite of exponentiation, which I think is 2 of n right there, which, as you can see, just flies into insanity really fast. So if you do 2 to the n or n factorial, you can see these algorithms. As the numbers look, the number isn't even 10, and they're flying off the chart. They're hard. They create a situation called combinatorial explosion. And think about, doubling the amount of pennies on a checkerboard every square. And by the time you get to the end, by the time you get to 64 squares, count up that number, and you'll know what I'm talking about. But the other side of the coin, which is a pretty good little pun there because I talked about coins on a checkerboard, is log n, which is a pretty efficient as an algorithm goes. I mean, as you can see by the chart right there, after constant time, log n is the way to go. Okay? So that's all Big O is. I'll promise you right now, you might get one insanely simple question on Big O on the quiz, and that's it. I just want you, like I say it all the time, I just want you to be exposed to this. I don't expect you to go get a book on computational complexity, and I'm not going to ask you about P versus NP and P space and all of those things. I just want you to be exposed to this and know about that algorithms that we code up in this fashion in computer programming are analyzed, and we do look at things like how long they take as their input gets bigger and bigger. Okay? So that pretty much, I think, is it for this half. What I'm going to do is I am going to do a video on recursion in a couple of nights, but I wanted to get this to you first. As far as announcements are concerned, I finished all of the midterm resource paper grades. I thought they were great. They were interesting. It was obvious you all worked with all the resources, so you got a whole bunch of practice. Super happy about that situation. If you did not get a grade from me, send me an email, please, because I believe I send everybody back grades, and I think they're all in my little grade book. So if you didn't get one, let me know, okay? I also today compiled up all of the grades for the 2 programming assignments and the quizzes, and you know what? At the end of the day, I was super happy with most of what I got, because Unit 3, as you guys know, was not the easiest thing in the world. It was next level stuff. You had to do a library, you had to understand functions, you had to understand file I/O, and you had to do it all in one big assignment and make all of that work. And if you think about it, well, about an hour ago it turned into November, but it was only Halloween yesterday, and you've only been doing this for 2 months. And now you're writing programs with libraries that are compartmentalized with functions to make more sense. And you do file I/O on real file data with random numbers. And things are, I mean, if you think about it, things are really moving along for you guys. And you're all doing a really great job. So the grades so far, knock wood, I don't think anybody's in danger of falling off a cliff. I know some people do warning grades and stuff like that. No need for me. You guys are all doing great. Everybody's engaged. I'm loving it. So good job. Like I said, watch this video. Keep going with Unit 4 slides. Read Zell Chapter 13. And I will have the assignments up probably by tomorrow. I believe assignment 1 is up there. It's a very simple little recursion function. Then assignment 2 will be a bigger assignment where you read in random numbers and then search within those numbers for certain numbers that I give you. And you'll do so binary, and you'll do so with a linear search, and then you'll tell me how many passes it took and things along those lines. Also, this week, I'm going to throw out a new wrinkle, and I'm going to throw out a third programming assignment. But this programming assignment is going to be optional. It's going to be an extra credit assignment worth probably 4 points, where if you load Matplotlib on your system and you do a simple program to graph the list of numbers that you're going to get from the second assignment, like you're going to clean up a list of 10,000 numbers. If you take that list unsorted and graph it, and then you sort the list and graph it, I want to see those two graphs. And you'll get that in an assignment explanation. I'll probably write that up tomorrow. So we're going to do an extra credit programming assignment this time around. I mean, if you looked at the Unit 4 slides, I don't think I had that little extra credit point in there this time. So this is going to be my way to get you guys a little extra credit. So some people, are teetering on the high BA area and want to say, hey, I'm busting hump. I want to show that I'm really working. Go load Matplotlib and do that simple. It's a simple program. The hard part is going to be understanding pip and understanding the package index with Python and loading that library and getting used to that process, because that's part and parcel of becoming a Python programmer, is finding that third-party library and installing it on your system via pip or via easy install or things along those lines. And it's not easy. It's a pain. I mean, your long-term programmers get driven nuts by dependencies and things like that. We call it dependency hell, where this needs a dependency, and sometimes the dependencies need dependencies, and it drives you nuts. There used to be a thing called DLL hell about dynamic linking libraries with Windows. And dependency hell is very similar to that, because sometimes it'll drive you nuts. Okay? Other than that, keep chugging, keep moving along. Do not, and I'll put a warning up for this, forget the deadline for the first part of the big final project, the proposal part. But I figure you guys will get going on that soon, and I'm looking forward to seeing those. I think there's going to be some interesting stuff. Do not forget that there is a TED Talk to watch. It's only 15 minutes, and it's pretty interesting. The apple pie thing at the beginning of it I thought was pretty cool. And just go give me a paragraph in the forums. Easy 5 points, gets you guys talking and gets you guys thinking about data science, which is the whole reason we learned Python to begin with, so we can take our data and analyze it and find things out about it in quick, simple ways, okay? Now, for the part you've probably all been waiting for. The Mets got clobbered tonight. Well, not clobbered. They were winning in the 8th inning, and they gave it away because our relief pitcher, Tyler Clippard, walked 2 guys. And then our closer came in, and he got a ground ball to second base. Daniel Murphy, who was the hero against the Cubs in the NLCS, missed the play, and the ball rolled into the outfield. So the Royals ended up, I think, tying the game, and then the next guy up got a base hit, and then they took the lead, and the Mets couldn't hit water if they fell out of a boat and ended up losing the game. I think they lost 5-3 at the end. That was the final. So they are down 3-1 in the World Series. They only have one more game left at home, and then they have to go back to Kansas City. Well, they won't go back to Kansas City if they lose tomorrow, but things are not looking good in Metland, which is bad if you're a Met fan. But it's good if you don't want to shave your beard off. So I promised I'd shave my beard off if the Mets won. But it doesn't look like the beard's going anywhere, unfortunately. So the things are crummy in Metland, but who cares? It's baseball, right? All right. You be good. Have a good night. Maybe Monday, Tuesday night, I'll do that recursion video, and I'll get it to you Remember, Unit 4 includes next weekend. So I'm not going to do the quiz or have the assignments due until November 9th. So you got another 9 days to puzzle things out. All right? All right, then you be good, and I will talk to you soon. Have a good night.